Hello. Welcome to another Sunday with HanoiDB. I hope you all are having a great day. Just fair warning, I am expecting a phone call, and I don't know if the person who's supposed to call me back will listen to the voicemail before they call me. So I may have to take a few minutes and talk to them. But hopefully we won't have that interruption during today's session. I announced it last week, started a new job on Monday, which is pretty exciting. Already had my trial by fire on Friday, dealing with an incident and debugging some code I didn't write. So that was pretty interesting. It's been a while since I've had to do that sort of thing. So it's both refreshing, but also exhausting. It was a very long incident. And it came down to some database issues. There was a contention on a single record, updating a single record. And so given the way that that is handled, it produced insane delays in reporting new data. And it turned out that this record didn't need to be updated with every API call that was made to this one endpoint. It only needed to be created if it didn't exist. Making that be a separate thing, where instead of kind of doing an upsert, it would only insert if the record wasn't there. So we also had luckily a bunch of SREs on hand to handle things. So that was kind of a wild way to start the job. But I'm learning a lot, and I'm really happy that I've got this new thing. So focusing back on what we're going to do today, we left it last time with a broken test. And the manifestation of that test was that we had a truncated is not the right word. We had a problem with the deleted key that was inserted. So I think I want to try a few things and see what the manifestation of this problem is. If it only happens to, say, the first key in a block, or if it happens to any key that's a tombstone, we probably want to figure that out pretty quickly. And then we can identify the area of the writer that is in error. So I think we should get to it. Let us get going. All right, so this was the test that we were doing last time, just to refresh your memory. We had some tests for the public API, but we did not do anything with before that. We did not do anything with individual modules, and I think that it's really important to test those too. So here we were doing a round trip test. So write some things to a file and read the file back to make sure that those things match up. Pretty straightforward conceptually. And so we created a new directory to store this one file. And then we are creating two entries, one which is a tombstone, so it's a deleted entry, and one which is a key value entry. And then we create a writer for this file that we have set up. And then we add the deleted, so adds to the writer have to be in lexical or byte order rather. That's the property of the B tree, and how the writer ensures it is that it doesn't accept anything that isn't in order. So here we're taking the deleted key, so we insert that first as a tombstone. Then we insert the key value 1. and then we close it and unwrap it. So now we have this file written test.data, and then we try to read it back with the tree struct that we had written very early in this process. And then we ensure that we get the key. So, you know, if you do get entry for this key, it's going to look like this key value that we entered. And then we discovered a problem. If we try to fetch the deleted entry, we don't get it. And so our next thing was to, okay, so let's just iterate over all the entries and see what they are. And then, you know, here's the failing assertion. So let's run this test again, just to make sure I haven't broken anything. Okay, so this fails, and we get, you know, we get none, right? For the key that we were trying to look up. We were expected this, right? So here's what we're getting. So it looks like the first 4 bytes of the key are sliced off. So we have a problem there potentially with either how it's being written or how it's being read. Or it could be both. The 4 bytes is especially interesting because to me that says, oh, you're expecting a size and we're not writing a size or something like that. Yeah, let's have a look at that. One thing that we could do also is, and this may be valuable for this may be valuable for inspecting the contents of the file. And maybe we should just do that. So here's what I was thinking. What we should do after we've written this, we should copy this file. So the data file, and we're going to copy to .test.data. And let's see. I guess we'll see where that ends up. And we need to unwrap that. Unwrap. Okay, so let's close this and run this test again, and maybe we can get the file here, and we can look at it with the hex dump. Okay, so we did get it. Same failure, obviously. Okay, I don't remember the hex dump. Can I man hex dump? I want to see what all these options are. Okay, so canonical hex plus ASCII. We probably just want. Actually, the hex plus ASCII will be useful because we'll be able to see the keys that we set up in the test and the values. Okay, so let's just hex dump capital C just for argument's sake. Test.data. Okay. So this is a very small file, obviously. So we do get the magic at the beginning of the file, which is these 4 bytes. And let's maybe fresh memory. So we do have deleted here. So let's see. That is. So it's 1, 2, 3, 4, and here's the 81, which is the magic number for that entry. You'll see later on um, there will be, real quick, let's jump back over here. So 0x81 is deleted, right? And we should see a 0x80 on the next line before. Yeah, so here's a 0x80. And this is the size saying there's the key is 3 bytes. And then they have the key and the start of the value, and it goes through to there. And then we have the tag end. So here after deleted, we have tag end. Okay. So I think that there's an issue with how we're writing. Because deleted is 7 bytes. Here's the end of that record, supposedly. Because it's always FF is the end, right? Okay, so let's look at, let's jump down here to entry since we're in this file. And we need to look at encode. And we don't care about the key value because we're pretty much certain that that's correct. Okay, so we need to make sure, first of all, the encoded size is correct. Interesting that it doesn't... What we're getting is TED, right? So in our test, what it's reading is 107, 101, 121, TED. No, that's not even correct. See, 107, 101. One, two, one. Yeah, it's not reading the correct bytes at all. It's not even close. I thought we were having it truncated, but those are completely different bytes. There's no 121. There's some 101s in here, obviously the E's. There's no 121 in this at all. Okay, so we've got a problem with either how it's being written, which it doesn't look like that's a problem, but we might have it with how it's being read. So let's look at and we'll simultaneously look at this code and also at the data that's actually in this file. So just for reference, I'm going to go ahead and pull up the design diagram, because we want to look at this, right? Now this has been changed. HAN2 does something slightly different. I think it has to do with I don't recall what the exact differences are. But we've got a length and CRC, and you would expect that those would pass. Okay, so there's all these blocks, and then there's the trailer, and we can look here and see that the trailer starts at byte 4, which we expect, which is the first byte so that the root position, 8 bytes within the file. So it's and this is big endian, so you're getting the smallest byte last. So it starts at byte 4, right? And then we know the bloom length is 0, and then there's no bloom filter in this, and then we have the required 4 bytes of zeros at the end. Okay. So, right, so we had 3, 4, 5, 6, 7, 8. And then we have a bloom length of 0, and then we have the 4 bytes of zeros. And here's the last entry in that block. Okay, and that first block starts at byte 4. So, now we have the block length, which is 4 bytes. Okay, so that's 29 in hex. And we have the level, which is 0, 2 bytes. And then we have 1 byte compression, 1 byte the tag byte of end. And then we have individual ones. Okay, so here we have the length, 4 bytes. That says the key is 8 bytes. And I don't recall whether that includes the tag byte. That may be part of the issue. Let's see. Yeah, okay, so we expect 8 bytes. It does not include the CRC in here. I keep flipping too much. I'm sorry, folks. So let's kind of put these side by side instead. Okay. So we have 8 bytes, and then we have the CRC32, which is 4 bytes. And then we have the deleted tag, 81. Okay. And then the key length, I think that's not correct. $64 would be D, would it not? 100. So 6 times 16 plus 4. Right. So there is no length. It's just the length of this. There's no keylen in this record when written, which is what we saw right, because we're not trying to read this. Yeah, okay, so this is just wrong. And what we need to be doing here is looking at there's a question in my mind about whether this is this is going to be an issue with compatibility. Oh, hi, Chris. Thanks for joining. Because I remembered that we were testing the other thing that we could do potentially here is go we're going to need to look at the Erlang code and see what it did, because this doesn't feel right. This is saying, take from byte 5 on. That's saying, bytes 0. Is that correct? Transit elements in at right. Okay, because we expect there's the tag, and then if it actually had the key length, which is strictly not necessary because we have the length of the whole record, right? and the key is only, this is redundant information, then we don't need this. What we need is split off 1. But if we want any bit of compatibility, and here we got this problem here too. Here the timestamp is there, and we want to split off 5, not because there's no keylen. This is for deletions with timestamps. We're not exactly handling those, but yeah. Well, we're not creating them in our code. Okay, yeah, I think this is the source of the bug. This is not an issue with writing; it's an issue with reading. And let's go back to our test and run that again. Okay, and it passes. So yeah, there we go. And I think we can do this. Okay, I thought that was going to be a more serious bug. I thought we were actually going to be writing things incorrectly. Now we may yet. This deleted may require the keylen in it. So let's. I do have the source up here. Let's look at the writer and see what it writes. So we need to jump down to, yeah, add key tombstone. This is what we're looking for. So let's go to append node. Yeah, that's going to be that. Okay. Okay, so that doesn't actually tell us what we need to do. Flush node buffer. Okay, so we need to go to encode index node and HanoiDB util. I don't know why that's in a util module. Feels bad, man. Okay, encode. Did I miss it? No. Encode index node. Okay. And we need to go to this. So this is looping over all the values that are in this node. So let's jump to crc encapsulate KV entry. Okay. Right, tag deleted and key. You note here that yeah, it's just not inserting the length. Whereas on KV data and KV data 2, yeah, you'll see that it inserts the length. So we're not breaking compatibility here. We are expecting the key to come immediately after the deleted tag. So we're not breaking compatibility there. It was just done incorrectly the first time around. And, you know, that stuff happens, right? So we don't need that. And we didn't need it here either. Okay. All right, that's good. Easy peasy bug to fix. It did take us quite a bit to look at the contents here and make sure that it's making sense. I honestly wish I were better at looking at hex dumps. and like knowing in my head, oh, this, hex code corresponds to this ASCII, but but I don't know that. So, all right, cool beans. Let's write some more tests for the writer. So here, this is an should be an easy one to do. And I think this is, you just do should panic. Writes are in byte order. So we can do some similar setup to this. Tests for the test god. Yes, exactly. It's there are some people who are very religious is not the right word. Fanatical, maybe, about tests. I used to be like that, but over time I have been moderating my position a bit. It's more that I want tests for my own sake, for a feeling of confidence in the code, and that means, some people are just like, write unit tests for everything, but integration or functional tests are hard. I kind of want to do some of everything. So note that these are more like functional tests. We're not testing the whole system. We're testing the writer, but in order to test the writer, we have to use some things from other parts of the code. So actually, before we do this, we're going to make a quick commit. Yeah. And we need to delete that line that copies the file to the local directory. Thank you, git diff. Okay. Okay. Okay, so we're going to do, this is session 14, fix reads for tombstone entries. Okay, source. All right. Yeah, I expected that you would agree there, Chris, but I'm glad you do. Don't write them just because you should write them. Write them to build confidence. And if you have some code that's really gnarly, write property tests. Yeah. I say really gnarly. What I mean is you need a high level of confidence in it, and the interactions are potentially complicated, which we might get to doing some of them for this. The challenge will be, I think the quick check for Rust doesn't necessarily have stateful tests, and so you kind of have to wing them. You have to do them yourself. I think there was a post by ReadySet a number of years ago about how they accomplished that. But yeah, we'll maybe want to look into that. And here's that phone call I was expecting. Give me just a few moments, and we'll be right back. Okay. How's that? We're back. Sorry for that interruption. Okay. So anyway, philosophically, that's my position on tests. Um, write the ones that are good for you. Don't be too obsessive. Okay. So we're going to test that writes are in byte order. This is an invariant that we need. So we can probably do something like copy pasta a lot of this. And then what we will do, in fact, here, we're going to do this, and we're going to reorder these writes. So the key value entry comes after. And I believe that, yeah, so add returns a result. So we should get a panic. And I think that we might be able to be more specific. Yeah, so we might be able to do error, out of order, right? And I'm going to have to refresh my memory on how should panic. Yeah. No, that's not what I want. There's a macro should panic. Boo. Checking for panics with should panic. There's a bit where you can, yeah, expected equals, okay. Yeah, we'll do something like that because we want to make sure that it says out of order right. And I guess it doesn't take the actual value there, it takes what the printed value would be. Okay, so let's test that real quick. Okay, call result, unwrap on an error. Okay, so, yeah. The other thing that we could do here is instead of saying should panic, probably the better answer is assert equal. So let's get rid of the should panic. I was trying to make it easy, but it actually doesn't make that much sense. So we expect it to be an out of order right. And there's an issue of there's not equal on that. So this needs to have partial equal, and EQ I think is sufficient. We don't have any floats in here. Well, that's not cool. Can we do partial EQ? No. And the issue is that these errors that we're wrapping don't implement partial EQ. Try from slicer. Now, we could do the other way to get around this is to say we can assert, let's do let last add, we'll just call it that. We can say last add is error. right? And we do last add unwrap error. We can do error toString, and we can say out of order right. Now we don't need this is error because we have the unwrap error. So why don't we do that? And why don't we inline that variable? We don't need another line. Okay, let's try that test. So just explain what I'm doing here. Again, we're still making the rights out of order. And the unwrap error makes sure that this should be an error, but also extracts. So if this is the error variant, will get the inner one. And you can see here, this is our crates defined error type, which we might rename at some point. We'll see. And then we're going to turn that into a string. So that's calling on, display, which is implemented for errors. We should get out of order right. Now this message may not be exact. There may be more details there, but let's find out. Well, I need to remove that. We can't implement partial EQ, so let's get rid of that. And try again. Okay, so that passed. We got bytes are in right order. The rights are in byte order. Okay. So now let's do something similar, right? We're just going to keep doing this. Maybe there's, I'm not sure if there's a way to do test setup like you would do in some other languages, and create this context that is shared. But here we're going to make sure that key counts. So we're testing key counts. So we're going to set this up just like we did before. We can delete that. Yep. And then we're going to do a write. So I'm going to copy these in. So we'll do this, and we'll do assert EQ writer dot. So the total count should be 1. And since we're in the same module, a child module, we have visibility to the parent. We can just directly access that field in this test. And we'll do a little check here. Value count. Now, this is, kind of checking both our method that we wrote as well as the internals. So we're going to do that, and then we'll write. So now we should have 2, and we should have 1 tombstone, 1 value, and then we'll writer.close.unwrap. Okay. Should be an easy test. Okay. Nothing failed. Okay, so this one is going to be a little bit harder. Blocks are closed when they reach 8 kilobytes. Let's go and let's do write an empty file. It's going to be similar to the round trip test. I want to jump over to this one because I think this one is easier to write. And we can make some assertions about the contents of this file. In fact, we might be able to even say exactly what some things are. But let's go ahead and get this in there. Okay. And then we want a writer. And then we're just going to close. Okay, so we can assert that we wrote an empty file. And then I think I want to do, let's just read the contents. Right? Okay, so then we can say, we can do a few things. So we can say that the we should be able to intuit what the length of this file is, right? So we need to unwrap that. Okay. Okay, so we're going to make an assertion that fails. But let's think about what the contents of this are. So there's the magic. So there's hand 2. That's 4 bytes. And then you're going to have the length of the first block, right? Like we saw in this diagram. So the block has length is going to be 0. So there's going to be empty block line. That's 4 bytes. And then there's going to be nothing there. And then there's going to be pad bytes. Remember, 4 0 bytes. There's going to be, because we have not implemented bloom filters, there's going to be a 0 length bloom filter. So we can exclude that. And then there's going to be bloom len is 4 bytes. And then root position is 8 bytes. So we should expect this vector that we just read from this file, this vector of bytes, be 4, 8, 12, 16, 24 bytes. Okay. The other thing that we can do is we can just in case we change what the magic is, let's call it magic. I think that we can possibly also use the tree from format to open this file and make sure that we can still read it even though it has nothing in it. And then we can get the root block potentially. We can see what this does. Now we probably have an issue in here in that we try to read the level and the compression, but if block len is 0, then yeah. Right. So this should fail to read. That is a problem we need to solve. But let's go ahead and put a to-do here. Fix tree from file / block from start to accept empty blocks. Now, let me take that back. I think we only need to fix block. So let's do, we're going to ignore it. We'll say tree from file. And we're just going to unwrap that to make sure that it can still read the file, even if reading the root block doesn't work. The other possibility is that we could look at reading the trailer, make sure the trailer can be read. Yeah, so the trailer, does the trailer implement partial equal? If it does, we can assert that. That would be good. Nope. That should be easy enough to add. Okay. So let's say let trailer. Now there's an issue here if these aren't public. These fields aren't public. We could do, let's just go with this for now. And let's see if I made any wrong assumptions in here. Okay, it's not working. So it got 26. What did we miss? We can start making some assertions here about the contents. Right? So we know that that block line is going to be 0. There's a question, so 26 rather than 24. Did I do the math wrong? No. 4, 8, 12, 16, 24. There's 2 bytes in there that we're missing. And I wonder if it's writing the level. Because block length bytes should include the level. Unless this diagram is wrong. Which it might be. Okay, so let's say level 2 bytes, and let's say 26. Okay, so this is block len 0. And here we're going to say that's going to be level is going to be 0, 2 bytes. And then we're going to have that's not the most riveting content here, folks. Okay, so we're going to have pad is going to be zeros, right? And then we're going to have something similar for the bloom one. So this is going to be 14 to 18 bloom length. It's like a co-working stream almost. Yes. You put in a lot of work for those this week in Bevies, man. Those are intense. Okay, so we got 8 bytes for the root position. And we know that this is going to be at position 4. So this is basically the contents of our file. Now I could like shrink this into one comparison, but I think having the fields broken out here matters. Okay, so what was that? Let's run this test again. And okay, so we don't need mute because that consumes. Okay. So this test did pass despite that warning. So there's a question in my mind about whether the level should be emitted if the block length is 0. And so then does this the root block right? So if we jump down here, so it is expecting to read exactly 8 bytes. The problem here is that if we're not writing 8 bytes, this is going to bleed into the padding. Now, I wonder what the Erlang code does on that. So let's look at the reader. Okay. So yeah, it got the root position, and then it goes into this read node function. Where is that? Read node. And it's just, yeah. I should have just jumped to that. Here we go. Okay, so it's not that. It's this one. Okay, so then it's just read a single node. Interesting. This may be the reason for the padding, the 0 bytes padding. So note that they're going to go ahead and read 6 bytes for the header of the block, even if length is 0. So this level, so it still has to read those 6 bytes, but that's the rationale for that padding at the end, right before the trailer, so that this 2-byte read will just get zeros if the the block has a 0 length. Now it goes, it says EOF is the return value of this. So if we jump back here, right, so that means there's no root node. I guess that makes sense. However, we don't handle that case correctly in our Rust code, because here we're expecting, excuse me, we're expecting to read 8 bytes, which should still be safe. Although I don't know that I've validated that in the writer, if there's an empty file, or that there's no entries in this. Let's see. Okay, it creates an blah 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 blah. Okay, and then it's got its state. So if we never call add, we just call close. Go to archive nodes. So if there's no nodes left, there's no guards on this pattern match here. So if there's nothing in here, it never added any block. So if it's undefined, okay, so it still writes the 6 bytes. So we did that correctly. And it's just that when it, in the Erlang code, it's only reading 6 bytes for the block. We're trying to read more. We're trying to read more aggressively. And I think that's an issue here. We probably need to read 6 bytes. And then this might be result of option self, such that we, if we find block length is 0, then we can return okay, none. That will change some things. Yeah, let's add that to our to-do. And I have a to-do comment in here as well, but so let me copy that from here. So we're going to fix block from start to accept empty blocks in the case of a file with no entries. This is standard edge case handling stuff. Okay, so it's there, but it's also in here, and we verified this test pass. So yep. Okay. Boy, I thought that was going to be easier. Okay, so solo internodes are pruned on close. This is about if you have um, written enough. No, let me take a step back. As we're writing the B tree, we are accumulating leaf nodes. So we're writing out leaf nodes. Um, and when we hit a certain size, so if we are writing a leaf node, we also create an inner node that contains the first key. Um, and I want to look at that code real closely, real quick. I think that what happens is we want to write enough to fill one block, which is related to this test that we need to write. Blocks are closed when they reach 8 kilobytes. Um, but what you don't want is to write, a non-leaf node in the tree that has only one entry in it. And that there was explicit code in the Erlang code to handle that situation. And it just says, whatever that thing with one poslin entry in it is, that becomes the root node if there's no if it's just sitting there by itself. So like you don't want that unnecessary indirection. It's not useful. Okay, so now the interesting thing is that will also handle the case where it's like a level 2 or a level 3. I don't know that any files written would be level 3, but I don't know, maybe they might be. The fan out on this is pretty big, but if you get to like a level 2 root node, so to speak, but it only has one entry, which is a node at level 1, that becomes the root. So this is just removing that, like, or saying that there needs to be a minimum fan out of 2. You can't have a fan out of 1 for any node. With the exception of if you wrote one key and that's a leaf. That is acceptable. But you can't have inner nodes with fan out of only 1. Okay. So how do we test that? Okay, so no, our inner nodes have fan out greater than 1. What a test name. Okay. So we need to write enough data to generate a solo inner node. I think we need to have some way of looking at the blocks that are in a tree. So we have entries. I guess we can get the root block. Yeah. Okay. So, yeah, let's. We actually have multiple cases here. There's some issues with computing this. We'll probably need to do some stuff. I think what I want to do is for this particular test, like this is the goal that we're going for, but how it's implemented, we can kind of test some of how it's implemented too. And I want to look at okay. So there's this yeah, add. So we're tracking a bunch of stuff in the struct. This add calls append to block. So that's an individual entry added. So that says we're going to add it at level 0. Okay. So this is semi self-recursive, I think. Right. So if the size of this block exceeds 8192, then we flush it. Okay, so it pops the last block off, and then it gets the first key of that block, and then allocates. Right, it allocates enough for the header and the trailer of this block. Okay, and then it writes the block size. We have some bugs to fix here. Obviously, you can't know the whole size if it's compressed. So you have to compress the entries first. We'll fix that later. Okay, so okay, so then yeah, so if we're finalizing this block, then what we get is you append a block, or you basically create a block or append to an existing block, one level up, right? So this only happens when you're finalizing a block. The interesting thing is that so we could approach this two ways. We could say that if you write something smaller than a block, you get only one block, right? If you write something bigger, or just enough to consume the entire size of the block, you write that block. But if you're not writing any more than that, so we need to kind of get pretty close to 8192 bytes on the last key, right? Then you will create an inner node that has the entry pointing to this finalized block. And then when we go to, so we can do that case, we can say, hey, let's write an 8 kilobyte block, and then let's check. There should be in this blocks vec, which we're kind of using like a stack, there should be a block with level 1. And we can call is solo inner block on it, right? And then when we close it, we should be able to read back the file. I should be writing this down. We should be able to read back the file and see that only one block was created. Okay. So I think I'm starting to clarify in my mind what these tests are. So this is like our goal here is block max block size is 8 KB. Okay. This is more about write 8 kilobytes. And then that should trigger it to be finalized and have an inner node created, right? That's what this is about. So we're going to write 8 KB of data, and then write 8 kilobytes of data, and then check that an inner node, inner block, inner node of the B tree was created. Okay. And this one is more about of data, then close. And we're going to check the contents of the written file to make sure there isn't an inner node, right? With a single entry. Okay, that's the difference between these, right? So test. Hello, Sean. Can you type? Not today. It's Sunday. Okay. So maybe let's do this, because we have to figure out how to write 8 kilobytes of data anyway. Maybe this is a function that we generate, right? Or we do once and then we reuse it. So, okay. And let's do writer. And we probably need like a start key of some sort. And maybe what we do is we kind of make the keys and values really regular. Maybe we can say it's a U64, and then we have like 8 bytes of key, 8 bytes of value. And this should return, I don't know, result of a U64. So what do we end with, right? And then we can chain those together, and we can do a test like, you know, if we write 16 kilobytes, then we should get an inner node, right? Because we have a fan out of 2. Okay. So let's figure this out, and then we can write these 2 tests, hopefully. Okay, so if we have a writer, and I think what we need to do is figure out what's the size of a key value entry for something that has 8 bytes of we can do this dynamically. Okay, so let's say this is a dummy entry. Hold on. Looking over here. Apologies for the split. We want to look at entry encoded size. Right. So, right. So this is going to be the size of an entry. Now we could just loop, or we could track Yeah, let's track. I think that's probably going to be better. So we're going to say let mute written is going to be 0. And that's going to be a usize just for clarity. We don't need to tell the compiler that because this method will return a usize, but we want to be able to track how much we've written. Okay, we're going to say while written is less than 8192, and the start. Let's just say key. And here we're going to return key. And this needs to be mute. Okay. This will be okay key. So now we're going to do, we're going to make an entry, key val, and then we're going to say, key to BE bytes, right? And we're just going to make the value be also that. And timestamp is going to be none. Okay, and then we'll say written. Well, let's entry size is going to be entry.encoded size. The other thing that we could potentially do is look at the writer itself. No, we don't track that. Okay. Since we're not doing any compression here, we don't have to handle. It's always just going to be flat. Okay, so what I'm trying to do here is go writer.add, and this like consumes that entry, and we'll put a question mark there so that we'll return. And then we'll say written plus equals entry size. Okay, so we're just looping until we hit interesting. Do back. I think this, I don't want to consume that. Yeah, that consumes. So I want as BE bytes. Does that exist? All right. Key.clone. Oh, but we shouldn't have to because it's copy. Okay. The other thing, the next thing we need to do, because we need to increment the key. Right? Yeah, this isn't the cleanest code, but we're going to use it. Okay. So this test, write 8 kilobytes of data and then check that the inner node of the tree B tree was created. So let's go ahead and do our dance of creating the writer. Okay. So now we're going to do write 8 KB, and we're going to pass mute writer, and the key we're going to start with is 0, and we're going to unwrap that because we want to make sure we don't actually care what the key is. This is just so you could chain them together. Okay. Yeah. Okay. So now we want to we're going to say there's one block pending. Okay. And then we're going to we'll get that block. We'll check that its level is 1 and that it has only one entry. So we can just use this function, right? Where were we? Okay. We don't need to see round trip. Writes are in byte order. Okay. So we're going to say assert writer blocks 0 is solo inner block. And I think that that's this function is so simple, I'm not going to test it. Some people will be like, oh, well, you need to test the different combination. No, like you can read this in one line. It's fine. We understand what the semantics are. We'll test it in context with other things. Okay, so let's do this. And okay, so this test passed. What could we do to make it fail? We could start a new block by writing another key, right? So now we could say, let's write another 8 kilobytes. So first, and yeah. Now we need to do key plus 1 here, honestly. No, it'll be incremented already, okay? Because it's incremented at the end of the loop, not the beginning. Okay, so now we've written another 8 kilobytes. We should still have only one block, right? But that block should have so the level is still 1, and we should be able to say there should be 2 entries, right? I think this is a pretty good test. Let's run it again. Okay, and so it still passed. So we did write 2 blocks. I think that's pretty good. Okay, so now that we have asserted that, we can go. Inner nodes have to have a fan out of greater than 1. So let's do all this, and then we're going to close. Okay, so we don't care about that key. Okay, so we wrote 8 kilobytes and we close. And here, this can come back over here, removing the split. Right, so let's do let tree from file data unwrap. So we need to be able to make sure we can read it. And let's do root block. Let's say tree.rootBlock. Unwrap that. And then we're going to say assert equal root.level is 0. So this is saying that, you know, this is solo inner block asserts that the level is greater than 0 and there's 1 entry. So we know that before we closed, there was a pending block to be written. And this is saying Okay, so we go ahead and close it. This asserts that it should be, the level should be 1 for the root block. But here we're saying it should be 0 because it doesn't make sense to have a root block with only one entry. That's not a leaf. Okay. What else can we assert? We can say that that start should be byte 4, right? Because it's the first block written. What else can we say about that root? Let's see. Is there great assert? No, we'll just say greater than or equal 8192, right? Okay. Now that we created that helper, this test was pretty easy to write, and we also wrote the one before it, which was potentially harder. Let's see if it passes. It passes. Okay. I think this is all the tests that we wanted to write. For so let's run the entire suite. Remember, the incremental merge takes a long time on nursery. And that one is lots of entries. That's a slow test. Okay, cool. Let's make a commit. So we're in session 14, and this is complete tests for the writer. Cool. So the merger is going to be very interesting to test. One thing that we could do potentially that we didn't do before is put this merger inside a box. That way we can address the size of that variant. It'll make the that method really interesting, the incremental merge. Might have to become a module function instead. Again, we wrote a really long detailed note about that. Yeah, that makes sense. Okay. So what would we want to, what are some things we would want to test? Let's just spitball this. Maybe we won't actually do it this time. We'll see. What are some things we would want to test? So we would want to test we'd want to test that, some basic things like if you have two trees with disjoint sets of entities, when you merge them, you get, and work all the way through it, you get a file that contains all the entries. Um, so like a completed merge with disjoint files, excuse me, disjoint key sets uh, results in a merged file with all keys. We would want to do things like so merging overlapping key sets prefers the newer file, the B. What else? Um, we want to do so incomplete incremental merges, return continue. We can assert the completion pretty easily in this first one, and we'll probably do the same here. What else? There may be a simpler one where if you have two files with 0 entries, you ended up with a merge of a file with 0 entries. It's not a particularly interesting one, but it kind of exercises this, where if there's nothing left in either of these iterators, then you end. Um, there's actually a bug here too, because step can be 0, 1, or 2. And the case where it's 2 is where the keys are equal. But that still counts as 2 keys processed because one of them is discarded. So we could probably fix our incremental merge to do like while steps is less than or equal to work, and have a mutable variable there, and instead of doing potentially multiple or like more than work done, right? Um, we would bump the loop variable basically by 2 instead of 1. Okay. That's not super important now. That's more like probably tuning. So let's do, these are more basic. Let's say completed merge returns complete incremental merge and consumes the merger. Okay, so these are more about the behavior of that incremental merge method. This is about what is the contents of the results. So I think we can set some of those up pretty simply. Yeah, let's do that. And what we might actually do as well is make this public. And this public. That way we can reuse this write 8 kilobytes if we want to do that. Yeah. Okay. We have about 20 minutes left in the stream. Let's go ahead and try to write some of these. So let's say complete incremental merge. Okay, so we need to write 2 files that we can merge. And maybe the most basic of those is like write 1 file with 1 key, 1 file with another key, merge them, and see what you get. Okay, so let's set up the A file. And we're going to have to do, again, this temp dir dance. And we'll do something similar to like this. Okay, so we're going to say we're going to say A10, right? And let's call this A data. Okay, and then we're going to do, we're going to need to name this A writer. Okay, so A writer add, and that's entry. And I need to use superstar. And we're going to have to use create format entry. We need to use create writer. Actually, we've already imported that, so yeah, that is not necessary. What's this warning? Yes, use temp file tempter. Hi Isaac, good to see you. Thanks for coming. Don't know what you've seen so far, but we have I'm sorry, we have fully tested the writer, and we did discover we fixed that bug that we saw last week. So I'm not sure if you were there for that, but pretty nice discovery that we had a bug that was probably from months ago. And let's see, timestamp is none. Okay, and we're gonna unwrap all that. Okay, so yeah, why is entry not? Okay, we're not explicitly importing, it's just inferred. We need entry, because we're going to need to use those. Okay, so we wrote 1 value to that, and we'll say a writer close unwrap. Okay. Now we're going to have to do the same for B. When we go to write multiple tests here, we will get, we don't need the dir. We will maybe extract some of this so it's less problematic. Or we'll just copy pasta and then there will be all of the context right there. Okay, so this, we don't actually care what the contents of this are. We just care that it merges, but so there we have an A writer and a B writer, and yeah, and so now what we're going to do is say a tree from file, a data. Okay. We need to open the files. Okay. So we need to open the trees. B data. Okay, so we should have two files that are complete, and they have disjoint key sets. So this kind of, you know, we could test this condition. The main thing we're trying to test here is that we create, we complete a merge, and the merge is consumed. So let us construct the merger. New, and we're going to say this is dir. The level is 10, and we get A tree and B tree, right? I named those explicitly so that it'd be easier. Okay, and this is return a result. It does, so we need to unwrap that. Okay, and now we're going to do merger, incremental merge. Here's the thing though, it doesn't need to be mute because it has to be consumed, right? It will be consumed by this step. So we'll say let result, incremental merge, and that should, we need to unwrap that, do we not? Yes, we need to do that. Okay, so there should be a, this should be a merge outcome. Okay. No, I think we're going to do let merge outcome complete count steps equal result, else panic, merge did not complete. And here we're just going to give this, we're going to give this like a big number even though there's only two keys. So we'll say 512, do 512 steps. Okay. So that means that we should be able to do assert equal count should be 2 and steps should be 2. Okay, the other thing that we can do is we can assert that that file exists. And we need dir join x10.data. So we're asserting both that it took that and it generated this file x10. Cool. We could go farther Okay. Let's see, open the trees and do a complete merge. Okay. All right, let's run this test. I'm a little bit nervous, but we'll see. Okay, it failed. How did it fail? Okay, so line 129. So it thinks it took 3 steps. I guess that's correct according to how we were doing this. Where if you hit 0, right? Um, it's fine. This again goes to the whole point of tracking the number of steps is how much work was actually done when it was not a complete thing. So I guess this is okay. We will want to maybe make a note to look at this. To do, does this value make sense? The answer is probably no. But I do recall something in the Erlang code where it would add 1 to that regardless. So that code though is a little bit gnarly, and I'm not really eager to get back into it. Okay. So let's do incomplete merges. So the way we can do this, I think, let's use create writer tests write 8KB. So we want to be able to write 2 files with 8 kilobytes in each of them, because we're going to want that for these things too. So let's do, first of all, before we go forward, let's do this. And I need to make sure that this test pass. Yeah, okay. So now it passes. It's just complaining about that. Okay. We're going to have to do a lot of this. Let's go ahead and make this test. Incomplete merges. Merge. Okay, so we need, honestly, we need all that, first of all. And let's do write 8KB on that. This needs to be mute a writer, and key will start at 0. Unwrap that. Okay. And then we'll a writer close. Unwrap. Okay. And then let's do the B. And then we're going to do these steps as well. Now we can say we can have it be disjoint. It actually doesn't matter. You know what? Let's not do that this time. Let's not do that. Let's have them be be overlapping. And the interesting thing here is that we don't really, yeah, we're not going to assert anything about that because it doesn't return complete. Okay, now we're going to have to do some of the same things that we did up here with these things, right? And let's copy this, but we're not going to. Okay, so we're going to make it merge like 5 keys. Or let's make it do 1 key, right? And then we'll say continue. Okay, and that's, I mean, we could do potentially, rather than this let, we could do assert matches. Although I almost never remember whether the assert matches. Yeah, I think that's a nightly still. Yikes. How many years has that been nightly? Yeah, it's not giving me docs on that. Why is this still nightly? Oh my gosh, it's just assert with matches. Yeah, I know. I know. Chris is saying nightly is like the staging area for anyone want this bad enough to actually finish it up. Uh, this is so minimal, in my opinion. But whatever. Okay, so matches takes the value, and then we want to match this. So and we can ignore the contents of that. Okay. Run that test. Okay. We have 5 minutes. Can we do another one? I think that we can. Yeah. I think what we can do is we're going to do something similar to this, right? So let's copy that, and we're going to do this. Okay. This one will be a little bit harder with how we've structured that, but maybe what we can do is we can make the value be different. Like do two 1 key files and make the value be different. I think that would be the answer. This one, and actually we don't need to write 8 kilobytes for each of these. Let's do something smaller. Let's actually do what this is. Okay, so I'm this is just a sanity check. Okay, so then let's okay, and we're going to unwrap that. So we want to read this. They have disjoint key sets. So we basically just want to assert x tree get entry, and here we're going to say let's extract this into a variable. Extract into variable, and we're gonna have to rename that. Rename a key. Okay, and we'll do the same here. I know this is dumb, but extract into variable, rename symbol B key, and here we're going to clone them because we're going to use them down below. Dot clone. Okay. So now we're going to say get entry a key. That returns a result of an option. So we're going to say unwrap is sum. And we're going to do the same for B key. Okay, so I think that that's, we know that each file has only one key in it. We know that the merge completed. We want to make sure that both keys are in the result. I think that's pretty straightforward. And then we'll wrap up with this one. We're going to do this. Test. Okay, merge over, what would we call this one? We called it complete merge with disjoint. Complete merge with overlapping. Okay, so here we're going to do, rather than B key, we don't care about B key. We're going to say A key dot clone, right? And then do we have equal on entry? I think we did that. So let's make we're gonna extract, oops, extract into variable, and this will be value.clone, right? Because we need to keep a copy of it. Okay, so now we're going to do xtree, so get the A key entry. And we don't need to unwrap. We'll just do OK sum. So this is going to be OK sum entry key value. And this is going to be A key. And it's going to be value, value, and none. So value, I think I also want to rename, just for clarity, to B value. That way we get All right, well, let's remove the results and the option. Let's do entry unwrap, unwrap, right? Okay. I don't know why that doesn't extend. Oh, well. Okay, so we're asserting that the tree has this key in it, that we can read that successfully, and that it has the B value. All right, so let's just run all the tests, and then we can close out the stream. It looks like our merger tests worked. Yes. This is feeling really good, y'all. I'm pretty happy about it. So love to see it. All right. This is a good place to end the stream. Let me make sure that we covered all of the tests that we wanted to write. There might be more that we could potentially, but that's good. Little verbose, that's all right. Tests are okay to be verbose as long as there's enough clarity in each of them. So session 14, tests for merger. Cool. Thanks for the kudos, y'all. I love it. Love it when you're active in the chat. So let's push this to main, and then we have nursery tests, we have writer tests, we have merger tests. We potentially go to level. Format is kind of too load bearing that it may be covered enough by everything else, but we'll see. And we have integration tests for the public API. So really good stuff, and we'll catch up next time. Thanks for coming.